So I want to start off by saying that we really need to blame Dan Wright for what follows. If you don't know Dan, here's a picture of Dan. Last year for YAPC North America, he asked me to give a keynote there, and he said, could you give a keynote on the features of Perl 6 that make life better, even for beginners? So on the basis of that, I more or less naturally decided that I would talk about these topics. And I started off by thinking about, well, what is it that beginners would do with Perl 6? And of course that depends entirely on what kind of beginners you're talking about. Most of us are still Perl 6 beginners, and we do particular kinds of things, probably the things that we were doing in Perl 5. Some people are actually beginners to the whole Perl community, and their first exposure might be Perl 6. And they're probably going to be doing whatever they were doing in other lesser languages. But what about people who are beginners of actual programming? What would they be able to do with Perl 6? So the great thing about living here in the future is you can go and Google a list of beginners in programming. And when you do, this is the list you get. So I thought to myself, okay, that's what I'll talk about. What were the things that they did, and what might they have been able to do if only they had Perl 6? So let's get straight into it. Let's start with Ada King, Countess of Lovelace, author of the first published computer algorithm. And again, through the wonders of Google, you could actually go and read the paper. I don't encourage this. It's not a fun paper. But it does have coding charts, so that if you happen to have an analytical engine sitting around, you can implement that very first algorithm. And that algorithm was for the computation of Bernoulli numbers. People know about Bernoulli numbers? You've heard the words? Yeah. This is kind of the weirdest sequence ever, the Bernoulli sequence, and we'll talk about it a little bit. Now, nowadays, you don't use an analytical engine to compute Bernoulli numbers. Nowadays, there are much better algorithms for it, like the Akiyama-Tanigawa algorithm. And this is that algorithm. I don't propose to go through the algorithm with you. It's not even that interesting. What's interesting is how much nicer Perl 6 makes it to write. So you have a couple of for loops there that make things really easy. From 0 through to n, through 0 through to n, going into the variable m, do something with n. The really nice thing is the next one down. From m down to 1, you will never have to write reverse 1 dot dot whatever again in Perl 6, because you can just count down in Perl 6. And better still, down the third one there, for correct 20. The correct operator in Perl 6 is the count up from 0 to less than operator. So you say for correct 20, you're saying for 0 through 19. Because like about 80% of for loops start 0 dot dot and then finish x minus 1. And you just don't have to think about that anymore. So you take a list, you apply that list one element at a time, binding it to a variable. Of course, what's really going on there is that we have lambda expressions. So this is not some syntactical magic thing. This is create an anonymous subroutine with one parameter, called m or j or n. Please choose better names for your parameters. And then the for loop is basically just a function that takes two arguments. It takes a list and it takes a subroutine. And it applies the subroutine to each element of the list. And this is not magic syntax. You can use this anywhere that you need a block of code. You can create a block of code with a named parameter. So you can do it with a map or a graph or anything else, and you don't have to use $_ anymore. You can give $_ a better name. The other thing you might be noticing is that my control constructs don't seem to have parentheses around the conditions or around the lists or around anything else. parentheses are just much less necessary in Perl 6 than in Perl 5. You can still use them if they give you a feeling of safety, but they're not necessary. Maybe the best thing is, in this algorithm, I have these variables, these arrays that I have to look up, and look how I'm looking them up. I'm leaving the @ sign there. And this knocks about 6 months off the learning curve of the language. You think back to when you were learning Perl 5 and you were having to work out, is it a dollar sign, is it an @ sign, is it a... you know, just to help you out, here's the table of which sigil you use in which situation, which seems to just be about random. Here's the table for Perl 6. 3 seconds, you've learned it. Saving you 6 months. So they're very cool. Another cool thing that you can do in Perl 6 is if you've got a double-quoted string, you can put a block of code in the middle of it. So not only can you interpolate arrays and scalars, as you can in Perl 5, you can interpolate entire subblocks of code. Which will mean you no longer have to break your string, put that little bit of extra code in there, and then restart the string and dot everything in between. Very, very cool. So let's look at that algorithm running in Perl 6. So here's the algorithm. Exactly as I said, here I am printing it out from 0 through to 20, and you print that out and it gives you the weirdest sequence ever. And there seems to be kind of a sequence to it, but then some of the numbers are just completely random, and every second one seems to be a 0 except the first second one. Okay. Now, the interesting thing otherwise about this, if you're a Perl 5 programmer, is that it's very, very similar to the code that you would have written in Perl 5. Here's the code that you would have written in Perl 5. And apart from those little syntactic differences and doing something truly horrible to interpolate the function call with a double-quoted string, and yes, you can do that, but please don't, then it's exactly the same algorithm. And if you run it, what do we get? Oh. Well, they're kind of like zeros. So if we look at the values that we got back from our Perl 5 and our Perl 6 version, we see that all the Perl 6 ones are right, some of the Perl 5 ones are right, the other of them are right-ish, and then something goes horribly wrong and we just go off at random. And of course what we're seeing here in the Perl 5 version is the cumulative rounding errors of this iterative algorithm just building up in the floating point numbers and sending it right off the edge. But why didn't that happen in Perl 6? Let me show you. The reason it didn't happen in Perl 6, we can see if we modify our calling of Bernoulli to say, and print it as Perl. Perl 6 basically has data dumper built right into it. And you can just get it by just saying .perl at the end. Dot is the way that we call methods in Perl 6 because we wanted to suck in all of the other coders from all of the other languages that use dot for method call. So if I do this and print it out again, you'll see that what it's actually doing is representing each of those values as a rational number. And it's doing that because we started off generating them by using a division. And so what it's using there is an arbitrary precision rational number to represent these things. So there's no loss of precision except at the very last step where, of course, it's converting it back to what looks like a floating point number. Now, you can do that in Perl 5. But don't do it like this. There is a big num pragma that says use extended precision or use arbitrary precision. And when you do that, it's better. And if you only look at this half of the screen, it's fine. What you actually want is this one, this pragma instead, which says use extended precision rational numbers, and then we do get the right answers, although they print out funny. But I would argue that Perl 6 is doing that better, because you didn't have to know that you had to do this, and you don't have to have a big rat in your program. So that's what I think Perl 6 offers beginners. For a start, it offers cleaner syntax, a more uniform and a more easy to learn syntax. But it also offers cleaner semantics. It has more do what I mean-ness to it. While we're talking about semantics, let's move on to one of the other beginners of programming, this guy, Alan Turing. Inventor, of course, of the Allen machine. You know the Allen machine? It's a great big long tape and a read-write head which is able to read a symbol, is able to write a symbol, is able to erase a symbol. What I love about the, Turing machine is that you can build it out of just about anything. If you've got some Meccano lying around, you can build yourself a Turing machine. If you've got some Lego, you can build yourself a Turing machine. If you have Excel, you can build yourself a Turing machine. And this, I thought, was going to be the weirdest suggestion that I gave to you until a couple of months ago when someone publicised that they had built a working Turing machine, not in Excel, but in PowerPoint. I would have bet that PowerPoint was not Turing complete. But my favourite implementation of a Turing machine is this one. This is not implemented in C++, this is implemented in the C++ template mechanism. This entire program consists of template declarations, and then in the main, you just declare a couple of variables. There's no executable code in this at all. The very act of compiling this runs the Turing machine for you, which pretty much tells you everything you need to know about C++. So how would I do it? Well, I would do it in Perl 6, and here is my Perl 6 Turing machine. You pass it a number of parameters. You have to tell it what state you're starting in, what are the rules for changing between states. You have to tell it where the head is, what the tape looks like, and when it should stop. And in Perl 6, we do that with just declaring parameters for our subroutine. Now, in modern versions of Perl 5, you can also declare parameters for subroutines, but not like this. For a start, I'm saying these are all named parameters. So when you call this function, you're going to be able to call it and name each of those things, and it's not going to matter what order you put them in. The compiler is just going to work out which one belongs with which. That in itself will save you about 6 months of debugging. You can make these things mandatory. Named parameters by default are optional because we mainly use them for options. But you can say, no, make them mandatory. And you do that just by screaming them. Normally, in Perl 6, we pass a parameter to a subroutine as a constant alias. The aliasing for speed, the constant for safety. But you can say, no, I want you to make a copy of them instead. Just by saying, it's a copy. For optional arguments, you can also give them any kind of default value, including default values which use earlier parameters, which means you can get most of your work done just in the parameter declaration. And then how do we implement a Turing machine? Well, it's an infinite loop, and Perl 6 has an infinite loop construct called, confusingly, loop. So you're never going to have to write while one again and just feel vaguely embarrassed by it. The first thing we're going to do each time through the loop is print out the entire tape, and we're going to do that with this one statement. In particular, I'm going to say, take the tape
get each key and value. It's an array, so the keys will be integers and the values will be the values in the tape. And then call a map function. Note that I'm doing this right in a double quoted string and I didn't even bother putting block quotes around it. You can just do this in Perl 6. If it starts with a sigil, as long as it finishes with a pair of parentheses, it's valid to interpolate. So every time you want to do a method call and interpolate it into a string, you can just do it right in the string. So what I'm going to do, I'm going to say, well, if we're at, the position we're at is the head position, then draw the cell with square brackets around it. And otherwise, draw the cell without square brackets around it. So when I run this, you're going to see that the head position moves across and looks really cool. And once we've printed that out, we're going to sleep for a little bit. Do you know what would happen if you wrote that particular line of code in Perl 5? Perl 5's sleep takes an integer value, and so it would round that to 0, and it would not sleep at all. Perl 6, we fixed it. That's what we were doing for 15 years. Just fixing all the annoyances. Then I'm going to have to look up what rule is going to be in effect, and the way I look up the rule is I say, okay, tell me what state I'm in, and I go and find the rule for that state, and then within that rule, which will be a nested hash, have a look at the head position on the tape. And if there isn't a value in that, then just go with the empty thing, which we're going to use an underscore for, and look up the rule for this current state, this current value on the tape, and do whatever you're going to do with it. Now, what you might do is discover there is no such rule, and the rule, when there is no such rule, is we die immediately. But assuming that there is such a rule, what am I going to do? I'm going to given it. And this is exactly the same as in Perl 5. I am simply making that thing that I found the current topic of conversation, in other words, $_. So what am I going to do with $_? I am never going to write $_. What I'm going to do instead is I'm going to call methods on $_, and in particular I'm going to do hash lookups of constant keys on $_. And in Perl 6, not only is the dot the method call operator, but there's a unary form of it. So every method you've ever called, you wrote object, dot or arrow, method name. In Perl 6 you can still do that, but you can also just say dot method name, and what do you think it defaults to? $_. So I can write what I mean. I mean, if you're coming from certain Microsoft languages, this will be very familiar to you. And you'll be shaking slightly. It's just a shorthand for writing some object that we call the method on. So what I'm going to do? Well, I only want to do some of my updates if a certain value is defined. So I'm going to take the head and write to the head whatever's to be written to the head, but only if there's something to write in the current rule. I'm going to change the state, but only if the current rule says change the state. And I'm going to move the head, and I'm always going to move the head, because if there's no move, I'm going to get back undef, and it's just going to do 0, and it's not going to add anything to the head position. And that's how you update a Turing machine. Now, the thing that I noticed when I was writing this example was I got kind of annoyed at this thing where I had to repeatedly say, I want to assign this value, but only if the value is defined. This is almost exactly the opposite of the // equals operator, which says assign it if the L value is not defined. This is assign it if the R value is defined. And you know what? We missed it. 15 years of practice and we didn't get that operator. But this is Perl 6, and it doesn't matter that we didn't get it, because you can just factor out that thing there, assign the R value if the R value is defined, and you can write yourself a new operator with syntax that Perl 6 has never seen before, basically saying, I'm going to create a assign operator, takes a read-writable L value, a read-only R value, and assigns to the R value to the L value if the R value is defined. And then back down here, I'm just going to use that operator instead. Whoa. And unlike Perl 5's operator overloading, it doesn't have to be one that Perl already knows about. You can use basically any sequence of Unicode characters. So if you want the smiley operator, you can have it. So let me show you this thing in operation. So here's all that code. And here's a set of very simple rules. This is the set of rules that Turing wrote as the very first Turing machine. And it's simply the Turing machine that takes a tape and duplicates what's on the tape. That's not a really interesting Turing machine. This is a much better one. Same Turing machine, that's the whole point of a Turing machine. But here's a set of much more interesting rules and quite a few extra rules. And here I'm going to set the tape up with just some random numbers. And watch what this Turing machine does. It sorts them and then gets excited. I love that. A sorting Turing machine. Now, it'd be much nicer if that was an interesting sort algorithm, but unfortunately, it's bubble sort. No, I did not attempt to implement Quicksort in a Turing machine. You can, but even I'm not that mad. So no one uses bubble sort anymore. We use algorithms like Quicksort. So you're probably expecting that now I'll show some picture of some old guy who invented Quicksort and tell you about him. And I am going to do that, but not this old guy, because Quicksort ain't that old. This old guy invented Quicksort. This is Tony Hoare, and he invented it in 1959, which is about the same time as John McCarthy was inventing Lisp. So let's look at Quicksort in Lisp. This is not Quicksort in Lisp. This is Quicksort in Perl 6. And yes, it does look scarily like Lisp, but indeed it is Quicksort. And when you run it, it quicksorts. Now, those of you who know something about Perl 6 know I don't think that there's a ka and a kuda or an nkunk in Perl 6. And you're quite right, there isn't. I had to write them myself, but how did I write them? In Lisp-like Perl 6. So if you're coming from a Lisp background, you can write Perl in your native language, more or less. But you don't have to. You can also write just a regular kind of quicksort that shifts off an element for the pivot, works out all the elements before, and Perl 6, by the way, has a generic before operator, so you don't have to care whether these are numbers or strings. It just does the right thing. And it also has a generic meta operator not, so you can write not before, and you get the two, and then you recursively quicksort them and put the pivot in the middle, and sure enough, it quicksorts. Or if you're coming from a Haskell background, you can write quicksort like this. You can say, quicksorting an empty array consists of returning an empty list. Quicksorting an array with exactly one element inside it consists of returning that one element, and quicksorting an array with extra elements inside it consists of using the pivot to do the recursive quicksorting on the excess list. So in other words, in Perl 6 you can make multiple subroutines which differ in their parameter lists and have the thing just do the right thing, and the parameter lists don't even have to be typed. They can also be just match the actual value that I'm getting. And this is an incredibly powerful thing, and yeah, it just quicksorts. So, this talk's supposed to be about beginners, and Quicksort is generally not favoured by beginners because they just never get it right. And I've taught a lot of beginning programmers over the years, and what I've discovered is that what beginners prefer is nondeterminism. So this, to me, appears to be the most popular beginner algorithm for sorting. This is the BOGO sort algorithm, and it basically goes like this. Until we actually have the list in order, and I'll explain how to work that out in a minute, take all the elements out of the list at random and put them back in the list. In other words, shuffle the list. And then see if we're in order. And if we are, then we can stop, and if we're not, then we shuffle again. And eventually we must be in order, you know, barring the heat death of the universe. And then we just return the list. Now, of course, Perl 6 can greatly optimize this algorithm for us because no one in their right mind writes x equals x operator y. We write x operator equal y. And you can do that even for method calls in Perl 6, which of course saves you like 5 characters of typing, which is the important thing. But the really important thing is it makes it very obvious that this method call is modifying its own object. And in most languages, there's not really a way of telling whether a method call that you make is simply going to return information from the object or modify it. But in Perl 6, we have 2 distinct syntaxes that you can use to make that distinction, which makes for better code. Now, how would we write in order in Perl 6? And the first thing to note is, yeah, in Perl 6, identifiers can have hyphens in them as well as underscores. And that is so nice. But how would we write the in order function? Well, in fact, we don't need to. It's kind of built in, and it's kind of built in with exactly the same number of characters. You write this. So not after is saying, well, it's an infix operator, A is not after B. But if you take any infix operator in Perl and you put square brackets around it, it becomes a prefix operator that applies to the list of arguments that you give it. In other words, writing that is a reduction over the list of not after. In other words, it's exactly the same as writing element 0 is not after, element 1 is not after, element 2 is etc, etc, etc. And of course, if element 0 is not after, element 1 is not after element 2, and so forth, the thing must be in order. And yes, in Perl 6, any comparison operator, any binary comparison operator, you can chain together as many as you like. So you can write 0 is less than $n is less than 1. And it just works. Why? Because we had to do something for 15 years and we fixed that. So in other words, you could just write in order and you could just make it a subroutine. Just whatever you want to do. There's more than one way of doing it. Now, the truth is, this is not a great algorithm. If you execute this, it does work, but notice the noticeable delay, the first you've seen from Perl 6. Oh, yeah, it's very, very slow. Sometimes. But on average, it's terrible. All right then, so maybe that's not such a good idea. But nondeterminism is a good idea. Is there anything usefully non-deterministic that we can do? And of course there is. We can play with prime numbers. So if you ask a beginner to write a subroutine that works out whether a particular variable, a particular value is prime, they're going to write something like this. Go from 2 to the square root of n, if you're lucky. They might say 2 to n minus 1. And for each divisor, return false if n evenly divisible by that divisor. Yes, Perl 6 has an is evenly divisible by operator, because we got sick of writing percentage denominator equals 0. So we just have it built into the language. And yeah, that actually works. Eventually. And we've only got an hour, so I'm not going to bother waiting till we see that one come out. So this is not a great algorithm. But conveniently, that brings us to this guy, who invented a great algorithm for primes. This is Pierre de Fermat, otherwise known as Fermat. And in 1640, he invented this algorithm, which is maybe the least obvious algorithm of all time. Basically, what this algorithm says is this. If you're given a number, just randomly choose a number less than it and raise that less than it number to your original number minus 1. And of course you're all thinking, well, obviously. And at this point you get a massively huge number. And then he said, and then the next obvious thing to do is to take the modulo against the original number that you're checking. And if you do that, and you get 1 as the remainder, then that number is very likely to be a prime number. And if you take another number and choose another random number less than it and raise it to that minus 1, you get an even bigger number in this case. Do the mod against the original. You get not 1, which tells you that 68 is not prime. So the only problem with this algorithm is that one word down there is probably prime. And all the other kids made fun of Pierre de Fermat, saying, what's this probably? And he said, all right then, I'll fix it. I'll show you how he fixed it. He said, the problem is, I'm not going to do the French accent anymore. He was really Australian. Look, mate, the problem was we're not testing enough. So he said, we're not going to pick one random integer, we're going to pick 100. And if we do this 100 times and we don't find a problem, then it's very, very, very probably. And they said, very, very, very probably? Yeah. So here's that algorithm. And the only difference is you do it 100 times, you randomly pick a number, Rj. Yes. Perl 6 uses Unicode alphabetics for its identifiers, so you can happily write R sub j. And in fact, you will be happier if you write R sub j. You will just feel so superior. And what do? We take R sub j, raise it to the power of n minus 1, and then mod it against the original n. And I could have just written that as R sub j to the n minus 1 mod n. But this exp mod is also built straight into Perl 6, and it is very, very much more efficient than taking two big numbers and raising them to an enormous number and then doing a mod. So when we run the very, very probably algorithm on a whole range of numbers up to big numbers, we discover, boom! Which is fantastic. and which might have been the end of this talk, had it not been for this guy. The villain of the piece, English of course. All the best villains are English. This is Robert Carmichael. Oh yeah, him. And what did Robert Carmichael say to Fermat, who at this stage had been dead for several hundred years? He said, all of these numbers and a whole lot more besides don't work. Gosh, said Fermat. And so it was not until 1976 when Gary Miller and then 1980 when Michael Rabin produced an algorithm, this algorithm, that overcame the problem of Carmichael numbers. And all I did basically was replace the way that they were guessing numbers. It just wasn't a random guess, it was a smarter guess, and once they found one, they would hone in on it in an inner loop. Now again, I'm not going to go through the algorithm, I'm just going to point out to you that we have some nice features in Perl 6 which allow you to say from 1 up to but excluding R. So you're never going to have to write -1 again anywhere in Perl 6. And in Perl 6, because we used Unicode as our source code format, it's perfectly possible to write $W squared. And it just works. And in my mind, this is enough reason to move to Perl 6. And then you have to go looking for algorithms that required squares. Or any power. It works for any power at all. That is just, I love that. That's so nice. So, when we run this one through all the really big numbers, boom, it's just as fast. But this one has an extra feature that Fermat's algorithm doesn't have, and that is this one continues to work if you remove the implementation. If you just remove the whole implementation of it and you run the source code again, boom, even faster. Now, this is not a general feature of Perl 6. It would be tremendously useful if, having worked out the algorithm, you could just remove it and that would accelerate. And yes, I am working on a module. The reason this works is that the Miller-Rabin primality tester is built straight into Perl 6. Because of course it is. We learned our lesson with Perl 5. You know, Perl 5 didn't even have max of a list built in. Perl 6 has everything built in. I don't think we have a Bernoulli function built in, do we? Yet. Anyway. So you're probably thinking to yourself, well, that's amazing, Damian, but you know what? Nobody cares about primes. That's true. You know, there's like 5 people in the world that actually care about primes. And one of them sitting right there getting very excited. It's nice to see him getting out, isn't it? And that's true. No one cares about primes, but I'll tell you what they do care about. People care a lot about prime factors. Who cares about prime factors? Well, the NSA does, and the CIA does, and MI6 does. They were the ones that first cared about it. Because in 1973, Clifford Cox invented the RSA algorithm. You all know how that works? It's based on the mathematical principle that if you've got 2 enormously big numbers, it's pretty quick to multiply those together. But if you've got one very, very, very enormous number, it's a lot harder to break it back out into the factors. And the bigger the number gets, the harder it gets to find the factors. Especially if you started with 2 primes, so there are only 2 possible factors of it. So what we're looking for is, given a very, very big number, very big number, how do I find the prime factors of it? Well, how does a beginner do that? Badly. The beginner's algorithm looks like this. You make a list of all the numbers up to the square root of n, and then while you still have possible divisors that you haven't checked, and while the n that you're dividing down hasn't reached 1, then you see whether n is divisible by the first remaining divisor. And if it is evenly divisible, you take that divisor as one of your prime factors. And what is take? Take is a built-in component of Perl 6 that collects values that you pass as its argument and funnels them back to the surrounding gather, where they are eventually returned as a list to you. So if you move to Perl 6, you will never need to declare an array and then go into a loop and push things onto the array anymore. You just put the loop in a gather, and within inside the gather, anything that you want to keep, you take. So we take that, take also returns its own argument, so what we can then do is divide n by that divisor, reducing the size of n. And eventually n is going to have to get down to either 1 or we're going to run out of candidates, in which case n itself will, what's left will be prime. Now, of course, if it's not evenly divisible, then that's not going to be a divisor, so we just get rid of it. And in Perl 6, arrays are objects, and you can remove elements of them by calling their shift method. So we keep doing that until we have gone through all possibilities, and then we just flatten down the factors that we got out of the gather and whatever was left over for n, and we remove any 1 from it. We only want numbers that are 2 or more, and we sort them because it's polite. And yeah, eventually Perl 6 will let us do that pipeline concurrently. Doesn't work yet, but it will. And when we do that, here's the algorithm. Here are some numbers. Show me the factors. Not going to wait for that one. So it works, but it's not very fast, and it doesn't scale at all. So how can we make this better? Obviously, non-deterministically. How am I doing that? I'm going to do it like this. I'm just going to randomly find a factor. Don't have to find all the factors, just let me randomly find a factor, and then I'm going to recursively find the factors of that factor, which is going to be quicker because it's a smaller number, and I'll also at the same time find the factors of n over the factor, which is another factor. And then how do I randomly choose a factor? By looping, randomly picking one number and returning it if it's a factor. So this is BOGO sort one level down. And of course, this being Perl 6, you don't have to write all that code to do that. You can just write this. Take 2 to the square root of n as a list. Randomly pick all of them. That is, shuffle them all. Grep out all the ones that are evenly divisible and return the first thing you got left. And you might think, oh my God, that must be much slower. It's not. It's actually faster. Because in Perl 6, almost every list you ever write is lazy. And if you do a pick on them, you get a lazy random list, and if you do a grep on them, you get a lazy random grepping, and then you take the first one, and it only executes as much as is needed to do that. And when you run that, when you run that, It's still slow. In fact, it's slower because it's making a whole lot of bad guesses. Except sometimes it's faster because it makes a good guess. So that's the kind of code you want to be writing. And if you're really lucky, it'll be fast on the day of the demo. So that's clearly not the kind of code that we want to be writing. But you know what? This is the kind of code that most people were using for prime factoring, except they weren't using this stupid algorithm. They were using horrible, horrible number theory to find better random guesses. So let me tell you about pretty much the current leader on the leaderboard of horrible numeric algorithms for finding primes. And that leaderboard is led by John Pollard. This is not John Pollard. There is no picture of John Pollard anywhere on the internet that I can find. So I just found a picture of Leonardo DiCaprio instead. Because I figure that when John Pollard got through working out this algorithm, this is about how he looked. And what he created was an algorithm called Pollard row factorization. And it was called that because he couldn't get away with publishing an article called Pollard Convergent Iterated Smart Guessing. So basically what he did is he took that random factor locating subroutine and he did this with it. He created this complicated algorithm which, because I care about you, I'm not going to explain, but which does indeed use the coefficient rho at various places, which gives me an excuse to show that you can write a $row variable in Perl 6. Now, that's cool, but it's also useful. If you can start writing your algorithms in the notation that you are used to understanding your problems, then it's much less likely your algorithms will be wrong. I also wanted to show you that Perl 6, yes, we have a greatest common divisor built into it, and it's not even built in as a function, it's an infix operator. But this is the line I really wanted to show you. X to the I equals x to the I squared plus 1 mod n. And now my life is complete. Subscripts and superscripts on the same variable. Life is good. So if we run this one, watch what happens. Boom! That is a good algorithm. That was worth being mauled by a bear. And it is a good algorithm until you get up to real-world sizes of data. And then once again, we might just scrape in under the heat death of the universe, or the end of this talk, whichever comes first. But I'm not going to wait for it. And that's the problem. The problem is that it doesn't matter how good your algorithm is, how efficient it may be, they still don't scale. Because it doesn't matter how number theoretical your algorithm is or how concurrent you make it, there's still not going to be polynomial time or indeed polynomial space. And that's a problem. Well, not for us. We're actually glad of that because it means that our encryption is probably safe. But it's a problem from the NSA and a problem from the CIA and from MI6, and they have all the money. So what do? They found this guy. This is Peter Shor. And Peter Shor published the first polynomial time algorithm for factoring using quantum computation. Now, I will admit up front, this algorithm is not for beginners. So I will simply show it to you and assume that you understand it. Well, you've had a European or British education. I'm just going to keep hammering on that. I am so annoyed that Brexit got through. But the thing I wanted to tell you is, yeah, while it's true that Shor's algorithm really isn't something that we'd want to go through in any detail here, quantum computing itself is actually quite easy, especially when I'm doing it. So the basic idea is simply this. If you have two possible outcomes, let's call them just 1 and 2, and you don't know which one you're going to get, maybe it's 50-50 you get either of them, then you can think about the system that you haven't yet observed the outcome of as being in like a superposition of those two. It could fall one way, it could fall the other way. And the probabilities don't have to be even. You could have another outcome which was 25% likely to be 2 and 75% likely to be 3. And when you superimpose those, you get something that's probably going to be 3, but there is a chance still that it's going to be 2. And it's perfectly possible to set up physical systems that represent this state of play using individual particles to do that. And then you can also set up systems that take those superimposed particles, which are not yet observed, so you have to do this in a dark room with a blindfold on. But if you can do that, you can set it up so that you have the equivalent of adding the two together. And what do you get? You get another component which has the addition of the values with probabilities which are the multiplication of the various probabilities of those values, because that's how probability works. You multiply. So you end up with very unlikely to be 3, much more likely to be 4, and reasonably likely to be 5. And you've got this whole system set up and you don't know what you're going to get until you observe it. And when you observe it, the superposition collapses down to something at random. And there it's randomly collapsed down to 5. Wasn't the most likely outcome, but that's what random means. Note what happened when we observed the result. See that the original values also collapsed. Because the only way we could have observed 5 if the original values were 2 and 3. Therefore, without even looking at them, we know what they are. And they can only be that one thing. Now, that's not going to happen every time. If we reset the whole system and have Leo look at them again, it's more likely to collapse to 4. If it collapses to 4, then the other two values will not collapse at all, because there were two ways of getting 4, 2 and 2, or 1 and 3. So they're still in their states of superposition. And the only way we could get them to collapse is to observe something more. If we observe one of them, then the other one is going to have to collapse consistently. And this behaviour of things only collapsing to consistent arrangements is known as entanglement. That the future observability of certain particles is constrained by what we've already observed. Or not if it was ambiguous what we observed. So why would you be telling me about this, Damian? Why is this interesting? It's not very interesting for addition, but it's real interesting for multiplication. If I was multiplying these things together, then if I took a superposition of all the possible factors and multiplied by all the possible factors, then that would give me a superposition of all the possible products. And if I then observed and saw that that collapsed to the product that I was interested in, then the others must collapse down to its prime factors. Holy crap. So if I've got the actual product, then I must have an actual factor and another. Now, there's no guarantee the bottom one's going to collapse to the right thing, but what do? You just run the experiment again. You press the button again, and eventually it happens. So I thought I'd better add quantum computing to Perl 6, as you do. It's not built in yet, so I wrote a module. Here's the module. You create states which have probabilities and values which exist with those probabilities and which you can then add together. and then you take two of those states and add them together, so they're in superposition. Now your Z value will be in superposition, and then you observe Z. And X and Y will collapse or not, depending on what happened. But what's guaranteed is they will always collapse to coherent states. And the only thing missing here is the fact that that's not how physicists write quantum states. They write quantum states like this, in the ket notation. And of course that requires a great deal more effort in Perl 6. You have to write a one-line post-circumfix operator that does that for you. So let's observe that. Here I have the states, here I have the Z. I also added a thing that you can't have in the real universe, which is you can observe the uncollapsed states. It's very handy for debugging of the universe. I observe X, and now I see what do Y and Z, observe Z rather, and see what Y and X do. And here, for example, I collapsed to 3, so Y and Z had to collapse to 1 and 2, respectively. If I run it again, Z collapses to 4, and now X and Y are not collapsed yet because we don't yet know what it's going to be, but as soon as you observe Y, then X collapses as well. And the only thing better than that, oh, I didn't show it. I wanted to show it. It doesn't matter. What's more interesting than that is what happens when we add a quantum switch. Because these are just assignments, we need control structures. So for that we need this guy, Erwin Schrödinger, and his famous cat in the box experiment. Everyone know the Schrödinger's cat experiment? Yeah. You put a cat in a box, you put some uranium in a box, you put a Geiger counter in a box, you hook the Geiger counter up to a container of cyanide in a box. He really needed help, did young Erwin. And if the Geiger counter counts enough Geigers, it causes the cyanide to be released and the cat's dead. And if it doesn't, then it doesn't release it and the cat's alive, and you arrange it so there's a 50-50 chance of that until you look in the box, the cat's both alive and dead. Now, Schrödinger proposed this experiment to illustrate how stupid quantum mechanics was. But it turns out that this is pretty much right. So here is Schrödinger's cat in Perl 6. You use the module, you say, well, it's 50-50 whether it decayed or not. The gas state then depends on whether it decayed. So we create a new operator called suppose that takes our unobserved value and says, if that value were observed to be true or false, then the corresponding state of the gas would be released or contained. So in other words, this suppose is more or less given this thing, when it's this, be that, when it's this, be that, but don't look. Don't observe, because that'll collapse the system. Or if you want to think about it, it's really the ternary operator for quantum. Except in Perl 6, the ternary operator has a different syntax. So, we do that, and now our gas state is entangled with our particle decay state. And then we do the same thing with a cat. If the gas is released, the cat's dead. If the gas is contained, the cat's alive. So now we've entangled all three of those variables, and what do? We observe one of them. And the others will then collapse to coherent states. So we observe the cat state, and oh, phew, it was alive. So what happens then? Well, that makes the probability of aliveness being 1, which eliminates the probability of deadness, which eliminates the alternatives in the previously entangled states down to the only ones that can be. And then when I observe those, they will be in that appropriate state. And sure enough, here's all that code. When we run it, every time you observe a dead cat, then you observe release and decay. Every time you observe a live cat, you observe containment and not decaying. Guaranteed. Every single time. So why is that cool? Well, it's cool for party tricks, but it's actually cool for real work as well, because you can use this to create prime factors. Remember this algorithm? This was the terrible algorithm where we used getting rid of bad candidates for random factors using horrible number theory. I don't like number theory, it's too scary for me. So instead I decided that I would do it by removing entire universes based on quantum mechanics, because that just seems like a much more reasonable way of doing things. Here's the algorithm, which is surprisingly not very scary. You entangle all of the possible factors. Entangle is just a shortcut for saying, make me a series of states, all of which have the same probability and which are all of the prime factors, all of the possible divisors rather. So you entangle that into a single scalar value which represents all of the possible and impossible factors. And then you just say, right, divide n by that. Now, I'm dividing a known value n by a superimposed value, so I get a superimposed set of moduluses. Modulos, I don't know. Whatever. But there's only one modulus because it's a single value, it just hasn't collapsed yet. And what do I do then? I say, well, suppose that the modulus was 0. In that case, it's true that this is a prime number. And if it's anything else, in Perl 6 when you want to say anything, you use the whatever operator. If it's anything else, then it's going to be mu, or mu, depending on where you're educated. What is mu? Mu is the most undefined value in Perl. And the effect here of mapping the value to mu is to eliminate it as a possibility. Same thing with the factor. Suppose the factor is prime, and I'm just going to use the built-in is prime operator there, then again, this is true. It's now not just a factor, but it's a prime factor. And again, if it's not, mu. Now, this is so common in this module that anything else to mu is the default, so you don't actually have to write that. You can just write this. So what I've done now is I've put constraints on how this factor can collapse. It can't collapse to anything other than 0 modulus and prime number, because that would be mu, and that would have destroyed the universe. And what do I do then? I just observe the factor. Literally by using the unary plus operator, which in Perl 6 is the convert to a number. And you observe that number, and then this happens. I didn't talk about the universe block that I had to add, because you really want your universal destruction to be happening in a lexical scope. Anyway, we run that, and sure enough, it's computing prime numbers and working out prime factors for me. And someone says in the front row, it's not really fast. That's because I haven't parallelized it yet. But I've run out of time, so I'm not going to parallelize it today, and it's his fault for making the complaint, because otherwise I would have got to... No. What I want to show you here is what's actually going on, which is even more interesting than quantum mechanics. What I'm really saying here is purely declarative description of what I want. In other words, the first thing is just let the factor be any of these. And let the modulus be n mod the factor. And it's required that the modulus be 0, and it's required that the factor be prime, and then just solve for the factor. And indeed, if I wanted to have written it that way, I could have. I would have just written 3 very simple subroutines that wrapped up the quantum mechanics in much less scary language. So this is the way that you can do purely declarative programming in Perl 6. And better than that, it's declarative quantum factorization. for beginners. So let me sum up. And one of the giants that I have stood upon for many years and that we all stand upon is this man. Yeah, absolutely. And for as long as he's been designing and implementing any version of Perl, he's believed that beginners need to have languages that have the right tools built in, so they don't have to pull them from a library or invent them themselves. But he's also believed that beginners need languages that get out of the way without too much syntax, without too much worrying about memory management or exceptions or other things like that. And he's also believed in languages that do what you mean, that if you write it, it's likely to do the right thing. But also in languages that do the right thing, because that's kind of nice, and that make it easier to do the right thing than to do the wrong thing. And all of those desirable characteristics of language culminate in his design of Perl 6. And so I truly believe that beginners need Perl 6 to get out of their way so they can learn how to program. And the great thing about it is, you know, Perl 6 is only like 18 months old officially. So we're kind of all still beginners in it. And that's my message to you. Why not begin today? If you want to play with all of the source code that I've shown you today, it's available online. So download it, play with it, try it out, do weird and crazy things with quantum declarative. It'll be on the video. If you want to know more about Perl 6, go to perl6.org. We've run about 5 minutes over. I apologise for that. And all that's left for me to say is thank you very, very much.